Boom. Okay, ladies and gentlemen, when I introduced agent-based models, I talked about them including one or more populations interacting in an environment, starting from some initial state, etc. They're interacting, and they're interacting via some sort of environment. And the environment we're going to be exploring today and next time as well it's what's called a network. So we're going to be able to hitch individuals up dyadically from one to the other in a network. And because time is fleeting, we're going to have to proceed quickly. So closing all your models, a file, new model, and this is going to be called initial network model. And the time units here, ladies and gentlemen, will be days, okay? Days here, okay? And initial network model, and I'm going to say CMPD 858, 394, and this will be fall 2016. Okay, here we go. Finish. Boom. Okay, so here's our model. Okay, now we are going to create a person class, and we are going to then add those persons into the model. So tell me, how are we going to do this? Remind me. You'll be needing this for your problem set. What do I do? Speak in one voice. Good. New, agent type, person. Okay. At least I heard one voice. Good. Excellent. Much appreciated. Okay, here we have person. Let's lend person a face upon the world, shall we not? Go down to... So how did I do that again? Just in case people weren't paying attention, I went up here, new, agent type, person, and then I did finish. Okay, go to person, make sure person is open. Go to the palette, go down here, drag in this person icon in a black suit. Okay, here's person. Okay, ladies and gentlemen. That's fine. That's all we need to do right now. I'm going to drag this property window down or drag it over so it doesn't occupy my screen. And okay, so I would advise that using that person shape. Okay, so ladies and gentlemen, now what I'd like to do is to add a group of these people to the model. How do I do that? Also important for your assignment. What do I do?
Create a population.
Indeed. So let's go to main. Double click on main. Let's go down main, and let's go drag person over to main, and we're going to call it population. And does that by itself create a population? No. What do I need to do also? Set it to be not a single agent, but a population of agents. This is what's called an embedded object in AnyLogic, incidentally. Could be a single agent, could be many. And to determine the number of agents, we're going to go, we want that to be something that instead of being hardwired, instead of being hard-coded, we're going to have it modified by experiment. What do we need to add? A parameter indeed. So let's go to the palette, and to main, we will add a parameter called population size. Okay? What sort of type is it going to be? It'll be an int. Okay, so an integer is something which will take on necessarily whole values, 0, 1, 2, 3. Yes, it could go negative. It'd be nice if there were a way of saying a non-negative integer here, but fair enough. And its default value, ladies and gentlemen, will be 250. And that's just the value if we don't fill it in for an experiment. Okay, for population, I would like now to set initial number of agents to be this dot population size. Okay. Now you could have left off this if you're so inclined, and I think I will do that for the sake of brevity. I'll just say population size. Okay. Okay, ladies and gentlemen. Next, I am going to actually run this model, and we will see a sight unfortunate to behold. What will we see?
Just one agent.
Okay, and where are the others?
Stacked on top.
They're stacked on top. ladies and gentlemen, they are stacked. You could see, and in fact, if you go up here, you could see the population is of size 250. There's a whole phalanx of them awaiting mobilization, but they're all stacked atop each other in an unseemly fashion. So if you go to population here, you can go move among them, and you could see they're all up here, and they all look the same. So we need to lend them some variability. So go to the population. There's two places we can do this. And I'd like you to go, I'm going to show you the more robust of them. Go to the population, okay? In main, the population. Click on it till you see the properties window of the population. I'm conscious of time here, and I'm moving quickly. So in the population, there'll be a thing called initial location. I'd like you to select in the specified point, and we're going to say uniform from 0 to this dot space width, okay? And for y, we're going to do similarly, but 0 this dot space height. Now, remember my injunction. Autocomplete is your friend. You can do this and press Control Space, and it will fill in these elements. It's a habit to which many of you, I believe, have warmed in other classes. Okay, so here we go. So please use often, please use early. Okay, ladies and gentlemen, I just built that model. So the x is going between 0 and space width, and y between 0 and space height. Ladies and gentlemen, build. Make sure it's a happy camper, and then run it. Okay, you should see something like that. If you do not, I suggest you pull up next to the person next to you and see if you can detect any differences in how you approached it. Do you see something like that? Okay, are we okay? Okay, let's, as a sanity check, let's go create a new experiment. You can go and do new experiment here, and we're going to say population size 10,000. Okay, 10,000. And you can go set the population size to be 10,000 for that experiment. Key point, don't go modifying your model when you want to change assumptions. Change assumptions in different experiments. It's orthogonal to the model. Same model, you can have different experiments. The model evolves, you can still run the same experiments. You go and you modify the model, you forget to change it back, and then you're in a world of hurt because you may be running experiments with assumptions that are different from what you think. Okay, so there's 10,000. You could see them crowded up here looking at you. Okay? Okay. Okay, ladies and gentlemen, fair enough. Okay, now we are going to do something rather different. We are going to go to person, and in person, you'll notice that there's this little figure, right? Now, if you notice, the person is defined as a group, and this makes it a little bit more difficult to manipulate, okay? So, ladies and gentlemen, what we're going to do is we are going to go in person on the left-hand side here in the hierarchy. We're going to go down, expand presentation, expand person to shape body. Okay? Now, in shape body, ladies and gentlemen, you'll notice there's this area called position and size, and there's something that says scale X, scale Y. Okay? Ladies and gentlemen, I would like you to do the following. I would like you to, for scale X, put 1.0, okay, plus, and we're going to take the natural log here. I think we need to do log here, okay. Give me a second. Is this nicely supported? I don't think so. Give me just a second here. I think we have to do it with log. Yeah, log. Okay, here we go. Log of this dot get connections number. Okay, this is going to ask how many connections do I have in a network. Okay? Okay, and we have to, in order to make this yield meaningful results even for people without any connections, we need to add 1 to it. If there's no connections, we want it to be log of 1. What's log of 1? 0. The larger the number of connections, the larger the log of that will get, and the larger they will get in terms of their scale. Okay? But they're going to have a minimum scale of 1. Even with 0 connections, they'll have a minimum scale of 1. Okay, ladies and gentlemen. So what I'd like you to do is run the model, make sure it's sane. Let's not run the 10,000 person model. They've looked at you enough. Okay, here we go. Looks okay? Okay or not? How did I do that? Maybe some people are still lost. Okay, I went to person. Ladies and gentlemen, I went over here in person in this side, and I opened presentation. I opened this thing called person, which is the name for the little visible indication. I went to shape body, and for shape body, I went down to position and size, and I entered this.
Why don't we just use the scale on the person group rather than in the...
It's a good question. There are additional features that come from doing it on this level, particularly when we want to change the color, which we're going to. And I believe if you change it for the group, you will not see those changes. I believe the scale might work for the person as a whole, and I would welcome feedback. But because we're going to be coming back to this again, I wanted to do it here. Okay? Okay, ladies and gentlemen. So now we have this. Now, this is what I'd like you to do. We're going to go in uncharted territory. Okay? Not quite where no person has gone before, but where few in this class have dared to tread. Okay, ladies and gentlemen, I'd like you to go to projects and go to main. And when main is selected in the properties window, I'd like you to scroll down to where it says space and networks. Space and network. Okay. And you'll notice here that there's something a bit unusual. There's a network type here. I'd like you to set this to be a distance-based network with a connection range, ladies and gentlemen, of 75. Now, I'm going to say something which you may find untoward. But don't worry, I don't mean it in a malicious way. But I'm going to use this to teach you a lesson, okay? So network type is distance-based and a connection range of 75. It's going to teach you a lesson of a mistake to avoid that I would like you to be able to be empowered to avoid. So, connection range of 75. Let's run this model. What do you think we will see? Oh, looks like it said scale X and not scale Y. So they all look distended. Ladies and gentlemen, what do you think that this suggests? Are some smaller than others?
Yeah,
Indeed. Ladies and gentlemen, there's variabilities. What does that suggest?
they're connected to the...
They're connected to certain people, but where is the network? The network we haven't set to display. To display it, I'd like you to follow my suggestions. And students often miss this up front. Okay? Okay, I'd like you to go to person. And I'd like you to scroll up to connections. Okay? So I went to person, I went to connections. And then in connections, you'll notice down here in the animation area, there's a thing that says draw line connecting agents. Do you see that? In AnyLogic, agents can have multiple types of connections. So I may have a familial relation connection. I may have a collegial relation. I may have a connection based on, research collaboration or something. Okay? So what did I do? I went to person. I scrolled up to see this area called connections. I selected it. It went down to animation. You might have to expand it. But fundamentally, I did draw line connecting agents. Do you see that? Okay, ladies and gentlemen, I'd like you to run the model. And behold. So what do we have now? What specter lies before us? Okay, yes, indeed, there's a graph. And the semantics of this graph were dictated by us earlier, but in a peremptory way. So we imposed a network type whereby people will be, a given pair of people, A and B, will be connected if and only if A and B lie within a certain distance of each other. Okay? Now you may wonder what that distance means. And you'll notice that in AnyLogic there's actually a way of indicating what the distance means in terms of meters or kilometers or feet. And you can actually ask it how far, talk about the physical distance. But right now this is a logical distance as measured by these connections here, okay? And actually if you look while you're on the canvas, it will show you the X and Y location as you're moving around, and that will give you a sense of scale. Each one of these little squares is, I believe, 10 in width, the really small ones. The big ones are something like 50 wide and 50 high. Okay, ladies and gentlemen, we now have a network. Okay, so we put people into a network, ladies and gentlemen, and now we have a clear shot to what we're going to do now. Ladies and gentlemen, we are going to put into place here a model of contagion. And this model, in terms of its basic structure, will be very similar to what we've done in system dynamics. But the assumptions, ladies and gentlemen, are rather different because this contagion will spread via the network rather than via random mixing. So let us press ourselves to that task. So if you go to person, we're going to go down to person, make sure person's in your palette as we will begin adding states with a measure of abandon. Okay, so if you go to palette and go to state chart palette, I'd like you to add in to person here. And here we're going to have, it's going to be called infection state chart. Remember that each state chart represents a certain concern. And if you have multiple concerns, it's in your interest to separate them into different state charts. It's more modular, it affords reasoning about it, can allow you to swap out representations for certain of them, and it means you have a certain economy of sort of characterization of a situation that's much better than describing all possible combinations of states, of sets of states. So rather than specifying states associated with age and infection status and having youngest infected, next youngest infected, next youngest yet infected, etc., you instead have two state charts, one for age, one for infection status. You don't have to deal with all combinations. Okay, let's drag in here. By the way, that's quite different than an aggregate model where we stratify it, and we have to deal with all possible combinations. We have to count the number of people in all combinations. Okay, so let's create the normal categories. Susceptible. Okay, I'm going to include exposed here. Okay. Those are people who are latently infected but are not yet infectious. Infective, and I'm going to set this, ladies and gentlemen, to be recovered. Okay, now we're going to set a set of transitions between them. And as befits the time, we will proceed post-haste. Okay, so I'm going to drag these between these. And you notice it's nice to leave enough room for them to show their icons. If I drag it too closely, the icons often get sort of not so obvious, but it's kind of nice to give them nice room. And finally, this being an SIRS model, I'm going to set this back here to loop back. Now remember, if you double click on these lines, you can bend them to your will. Okay, so double click and you can put these kind of blibbits in it, which allow you to shape it in more aesthetically pleasing lines. Okay, ladies and gentlemen, what sort of semantics are associated with these transitions now? What sort of transitions are they? Well, it turns out they're timeout. That's shown by the little clock. We are going to put in place something else. So ladies and gentlemen, I'd like you to set, let's start with this one that's indicated here. This is going to be a mean infection time, ladies and gentlemen, of 1 over some mean recovery, mean infection duration. Now, I could call this, and I'm going to call this transition recovery, and it's good practice to show the name so that there's a little check mark here, show name, okay? And ladies and gentlemen, I am going to go and do something that may be a bit unexpected, but such is life in this class. Okay, I'd like you to go to main, okay? And I would like to add in a couple parameters. Okay, one parameter would be called mean infection duration. Another will be called mean latency duration. Okay, and then another will be called mean duration, mean immunity duration. Probably I should have called a mean duration of infection, mean latency, mean duration of latency, but that's fine. Okay, now, ladies and gentlemen, a point of note. These can all be represented as doubles, but we know something about this. It's not just your average continuous quantity. What particular types of things unite these? All of them are characterizing what? Times, indeed. Ladies and gentlemen, times, indeed. So let's go in the types here, specify that it's a time. And we'll specify that time units is days. And mean infection duration will be 10 days. Okay? It's kind of nice. It documents the units here quite explicitly. We saw it within system dynamics. Mean duration, so mean infection duration, 10 days. Mean latency direction, or duration, 3 days. Okay? Mean immunity duration, we're going to set it, ladies and gentlemen, to be days, and in terms of days, it will be 50 by default. Notice that's the default value. What could override this value? This is the default. Where could we specify a different value, a different assumption? Indeed, and that's exactly the reason I'm putting these in main. You might argue, and I would not disagree with you, that conceptually these belong in person. After all, they're about a person. But because they don't vary between people, and because we want to vary them across experiments, we're going to keep them in main. And it's a bit of pragmatism, which I'm only marginally comfortable, but I'm going to adhere to it. Okay, ladies and gentlemen, so given that we have a mean infective time, a mean infection duration, what is the rate going to be from infective to recovered? If we represent it as a rate, what would the associated hazard rate be? 1 over main dot mean infection duration. Autocomplete, ladies and gentlemen, is your friends. Notice again, we can ask it to convert that in time units, but we're just going to choose the one that's referring to the simple variable. And you notice that we could say per day here. Okay? Great. Similarly, ladies and gentlemen, from exposed to infective. Okay? Okay, so this is going to be called becoming infective, and we're going to show the name here. And ladies and gentlemen, this will be a rate transition with rate 1.0 divided by main dot mean latency duration. Great. And finally, for this one here, losing of immunity. We're going to, we'll say waning immunity. It'll be show the name, okay? And the meantime, or it'll be a rate transition. Maybe we'll keep it as a timeout. Let's keep it as a timeout, and it will be, is it 1 over, or is it actually just main.mean immunity duration? If it's a timeout, it's actually looking for the time unit, a time, some unit of time, some amount of time. So it just mean immunity duration. Great. Okay, now, ladies and gentlemen, we're a lot of the way done, but we have some important features to put into place still. And I want to illustrate how this model works right now. Okay? And I sit before you remiss, because I should have emphasized something. So temporarily, and this is kind of a nice feature of AnyLogic, I'd like you to go back to these here, okay? And I'd like you to set each of them to temporarily just be a timeout, okay? Just set it to be the timeout. You notice it will still remember your rate. If you go back to rate, it will remember it. So don't worry, you won't lose your work. So each of these is a timeout. Are we okay with that? Ladies and gentlemen? Timeout. Okay, next, to bring home this point, I'd like you to drag in a variable. Well, you're going to tell me, how if I want these people to change color? How am I going to illustrate that? We've done it before. What's an easy way to do it? Yeah, we could add in a variable. We'll call it color. And its type will be other, and color with a capital C. We did this last time, remember? There was an issue with the compilation, and it caused distress. The initial value will be black. We added in color, type other, and it'll be color with a capital C, and its initial value is black. Do you see that? Got it or not? Okay, good. Ladies and gentlemen, now we go back to the shape body. Under person, presentation, person, shape body. And now, under fill color, we're going to change it to be a dynamic value here with value equal to color. My color, okay? Okay, ladies and gentlemen, color. The value of this variable will be used. Notice that this is a declarative specification. We're actually not telling it, set it to this. We're actually just saying, make it such that this stays consistent with the color, which is a rather nice feature of AnyLogic. It's an example of its declarative features. You say what you want, it takes care of the how, which has some advantages to recommend it. Now, ladies and gentlemen, I'd like to go set color in a most imperative fashion. Where can I set the color here, ladies and gentlemen?
On the entries.
In the entries to each of these guys here. So, ladies and gentlemen, for susceptible, we'll set color to green. For exposed, we will set it to yellow. For infective, ladies and gentlemen, we set it to red, and recovered to magenta. Susceptible, we will set color equals green. Don't forget your semicolon there. It's a command, it's a statement telling it, do this. Color equals green. Exposed, color equals yellow. Infective, ladies and gentlemen, color equals red. Recovered, color equals magenta. What will I see when I run this model?
So just kind of cycle through colors.
Yeah. So cycle through at an individual level. What will we see at a population level? So I would remind you, how did we do this? We went to shape body. If anyone's behind, we went to fill color. We had to press this thing here to change it. We entered color. We added this color variable, right? Type other color, black here, and we went through, set this to green, yellow, red, magenta. Okay, so let's run it. Here we go. Now, ladies and gentlemen, what's happening?
Having a disco.
Okay, so very good. Okay, so it's exhibiting flashing behavior. Okay, so ladies and gentlemen, let's change these back. Why is it flashing in that sort of synchronized fashion? These are all the same timeouts across all agents. Let's change these to back to rate transitions for both becoming effective and recovery. Go back to rate. Rate, ladies and gentlemen, rate. Do you think it'll be synchronized now?
No.
Indeed not. Now, even to my impaired aesthetics, there's a somewhat unseemly character to those depictions, and I'm troubled by it. So, ladies and gentlemen, since we know how to get back to shape body with such ease, let's go back there and change the scale X and scale Y to be the same. Because all that's happening is we're stretching the scale X without correspondingly stretching the scale Y. And it's leading to this most unpleasant of appearances. Okay, so let's turn this back and let's watch this. Okay, here we go. Okay, now that affords us a better glimpse, but really this scaling is getting a little bit tiresome. Let's get rid of the scale altogether. Just have everyone be scale 1. It served its purpose. It let us know that there was a network, even though we hadn't connected things. So now that we're beyond that, we can enjoy it. We can enjoy it in a more comfortable perusal. Okay, so ladies and gentlemen, but some of the most important features are gone. Why isn't this yet an infection transmission model? What's missing?
Susceptible rate to exposed.
Okay, good. So this rate here, what needs to be happening for this to be an infection transmission model?
Perhaps it should depend on the network.
Indeed. Okay. So ladies and gentlemen, we're going to change this susceptible to exposed to be not a timeout transition, not a rate, but a message transition. When they receive a message, it'll be via the network, and they are going to then transition from this state to this state, okay? So I just changed that. It's a third type of transition of which we will be exploiting. Next, ladies and gentlemen, I would like you to go to Palette, and I would like you to drag in here a transition from the infective state to the infective state here. Like that. And it should be inside of the infective state. Believe it or not, it matters. Okay? This transition will be called contact. It'll be a rate transition. And once again, we will need to go back to main to add in a parameter. Okay? So in main, we're going to add in a parameter called contact rate. Now, ladies and gentlemen, we added these other parameters and we delineated them as time. What sort of parameter will this be? If we look at the buffet of options, which one of them beckons us?
A rate, perhaps.
A rate indeed.
It's an option.
It'd be a rate per day, ladies and gentlemen. And the rate per day here is going to be a rate of 1 per day. Okay? One contact per day. Okay. Okay, a rate of 1 per day. So it's a rate per day rate. Next, go to main and go back to that contact transition. And ladies and gentlemen, the rate is going to be given by what? Anyone? Yeah, main dot contact rate per day. And now comes the key point, the key missing element. There's going to be an action. If this simply fired by itself, it wouldn't do anything. What needs to happen?
Send a message.
Send a message. Okay, so good. So ladies and gentlemen, we're going to say here that we want to send a message. Now, it turns out that there's several ways to do this in AnyLogic, but we're going to set it to be send to random connected. Okay? And we're going to send the message, and don't do this on a regular basis, infected, okay? Infected to a random person, okay? Now, the reason we can get away with this is because there's only going to be one type of message. We're in the final minutes here, ladies and gentlemen, the final minutes. We'll build on this model next time, but we're in the final minutes of it. And you'll build on this model in a take-home exercise. Okay, send to random connected. Okay, great. So, ladies and gentlemen, I'd like you to run this model. And you'll tell me, what do you think will happen? Nothing. Why not?
There's no initial infected.
There's no initial infective. Okay, so ladies and gentlemen, we have many ways to address that need. Let's go to projects. Let's go to shape body. Time is of the essence. Let's go to shape body. We're repairing to shape body on many occasions. And I'd like you down in shape body to go find in the advanced area. There's something called OnClick. Do you see that? So I'd like you to here do the following. Type this dot, I'm just making it explicit, send. And if you say send, you'll notice with the send, if we look here, we send an object to a certain destination. The message is going to be infected, and the destination will be this. Who am I infecting? This guy is infecting whom? Himself, indeed. Okay. Now, it's just a way of starting that infection when we click on someone. So shall we run it? So build early, build often. How did I do that? I went to shape body. I scrolled down to the advanced area. I went to this OnClick, and I said this dot send infected. So when I click on it, we're going to send them a message, and we're sending the message to this. Okay, are you ready? Here we go. Okay, ladies and gentlemen. What do we see? Maybe slow it down a bit. What do we see happening over time? Most people are at any one time seem to be in what state? Why is it that if I run it long enough that it seems to go occasionally to what? Is this a stable or an unstable equilibrium? This isn't equilibrium. It's a disease-free equilibrium, isn't it?
Yeah, unstable.
Nothing changing. If I go click on this guy, hey, come on, come on. Oh, the simulation ended. It went to time infinity. It said, hey, there's no more work to do. Okay, yeah, let me not turn it off this mode, okay? So here we go. I'm going to click this one. And sometimes it doesn't catch. Do you see that? But sometimes it catches. Why?
Not many neighbors have a lower chance.
Yeah, okay, so there's stochastics involved, right? You'll notice there's also seems to be a situation where we have almost waves of infection sweeping through this population. There seems to be some sort of spatial pattern here associated with it. And we're going to explore some additional features of this next time. In the meantime, I'm going to ask you to build a little bit on top of this for Thursday so we can have some depictions of what's going on, and you can look at some of the temporal patterns coming up. Okay, so that's all for today. Thank you very much for your patience. That should give you the key understandings needed to get started on all parts of the problem set and to pursue problem 3 in a steadfast fashion. So thank you very much, and we will see you on Thursday, and I'll let you know when I post a take-home exercise.
We do on